Okay, good day, everyone. And we're on chapter 10, section 1, where we're going to start talking about radical expressions and radical functions. So recall the radical sign. We're talking about square roots, and inside could be a number. Let's say that is any number or a number, which is the radicand. This is the radicand, and the symbol there for square root is the radical sign. All right, well, we're going to talk more about this as we go. I'll get into it, the basics anyway, deeper as we get deeper into the chapter. But for right now, let's move on to our introductory examples. All right, here we talk about the square root, opposite. Get rid of that. Opposite of squaring a number is taking the square root of a number. The number b is the square root of a if b squared equals a. Now I know these definitions in mathematics is confusing, so we'll simply say if I've got, I'll make a little t-chart here to help us out, and this is b and this is a. So if I give b a value, let's say if b is 5, then what would a be? So I substitute 5 for b, and that gives me 5 to the second power, which equals 25. So when b is 5, a is 25. I could do this with any whole number, of course. I could say when b is 2, then a is going to be 4. How about when b is 3? When b is 3, a is going to be 9. So therefore we say the square root of a, that's this part here, the square root of a is b, which is 25. That number squared. Okay, here are some elementary problems where we take the square root of 49 is 7 and the square root of 25 over 16 is 5 over 4, etc., etc. So just as a reminder, how do I find the square root of 49 if we don't know? If we don't know it? Well, which is huge here is I want to know how to do the factorization, the prime factorization of values. Okay, as long as I know how to do this, then we'll be able to figure out any root problem that we're encountered with. Okay, so the square root of 49, the first one, I would take the 49 and do the prime factorization of that. And this is easy because it just becomes 7 times 7. That's the only two factors I know, other than the number and 1, the number itself and 1. So here I have 7 times 7 is 49. I want the square root of that. So you'll hear me say this, for every 2, I'm going to take out 1, because the square root means I have an index number of 2 here. Meaning I want 2 of the same values that equal 49. So 2 equal numbers that equal 49. In this case, it's 7 and 7. So it's the square root, so the index or the root is 2. So I say it in this way, for every 2 factors of 49 that are the same, I'm going to take one of them out. And I do take it out, and that's what's left is the square root of 49 is 7. 25 over 16, I could look at it the same way, is the square, the factors of 25 would be 5 times 5, and that would be over the factors of 16, which is 4 times 4. Okay, so for every 2, I'm going to take 1 out. For every 2 in the denominator, I'm going to take 1 out. So I end up with 5 over 4. Kind of telling you the back way of how to solve these problems. This is a negative square root, so notice the negative sign is on the outside. There is no such thing as pardon me, a negative on the inside of the radical sign when it is an even root. So this is a square root, meaning an even number 2 is here, so this is not possible. Whenever we square a number, we always get a positive value, so this is like the opposite of that. So what we have, in other words, is if I have a negative square root, it's written this way. The negative really has nothing to do with it. How about D? I have something a little bit larger. The square root of 9x to the 10th is 3x to the 5th. If I was figuring that out, I would do something like the 9x to the 10. And I could do the prime factorization for this. So if I did that, it would be 3 times 3. And then the factors of x to the 10 are 10 x's. I'm going to do it the long way here for you, just to kind of give you a little deeper, richer knowledge about what's going on. 6, 7, 8, 9, 10. There. So here I have 10 x's lined up. This is a case of prime factorization. Everything's multiplied or broken apart. All right, so for every 2 of each of these items, because my index here, it's not written, but we know it's 2 with a square root. So for every 2, I'm going to take 1 out. So here I've got 2 3's, so the 1 comes out. I'll bring it out here. I've got 2 x's here, so one of the x's comes out. Another 2 x's here. I'll put another x here. Sorry for my sloppy writing. Here's 2 x's here. Goes here. And finally, one more set of 2's. For every 2, I'm taking 1 out. So all this simplifies to be is 3x to the 5th. Or you could take this even number, the exponent, divide that by 2 and get x to the 5th as well. But again, if you're starting out, you're confused, you're not sure of what's going on with square roots, this is a basic lesson here for you. Okay, you'll see me do this often because students struggle with this, and I want everyone to be successful with understanding what is happening in this chapter. All right, move on. Okay, next is approximate the square root of 5. This is calculator work when we're going to approximate the square root of 5. There's a difference you'll see in the exact value and an approximation. So you'll use our calculator for that. Learn about your calculator and how to determine what the buttons are that you push to plug in the value for the square root of 5. And you'll see, well, I'm going to have an approximation. And notice the symbol here, the approximate symbol. It's not the straight lines equal sign. This means, these little curly lines means approximately 2.236067977. Okay, and then many times on these particular problems, you'll have to round it to a certain place value column, which is, something else that you have to sharpen up on. So if I wanted to round this to, let's say, the hundredths column, here they're saying to the 3 decimal place. Let's say if I say to 2 decimal places, which is the hundredths column, then what I do is I underline the number in the hundredths column, and then the number to the right, called my neighbor, depends on my neighbor if it's going to stay the same or move up. So in this case here, the hundredths column is the 3. I'm looking to the right 6, so that means I'm going to increase the 3 by 1. So this is going to round to be 2.24. And that's rounded to the nearest hundredth. This is rounded to this in the original problem here, it says round to 3 decimal places. Well, in that case, here's the 3rd decimal place. And then the number to the right is a 0, so that means the 6 stays the same, which they've done successfully here. Okay? Next. All right, next we're talking about the cube root of a real number a. Cube root of a. Notice the index number is 3. For cube means 3. 3 factors. Okay, and cube root of a equals b only if b cubed equals a. So let me say that again. The cube root of a equals b only if b to the 3rd equals a. Note, very important note here, a is not restricted to non-negative numbers for cubes, because you could have something like -3 times -3 times -3. These are 3 values of -3 that equals -27. So the cube root of -27 is indeed -3. So I can have a negative in that underneath the radical sign. Cube root of -27. Because this index number now is 3. What are 3 values of 27 that equal -27? What are 3 values of -27 that and the numbers are the same, identical? All right, we'll go over some of these here shortly. All right, so that's an important note to take, so remember that, the cube root. Okay. All right, let's do some examples. As we did earlier with the square roots, this is to find the I'm having a hard time here. This is to find the cube root for each of these. So the answer is here already, and more importantly, how do we get to the answers? Taking the backdoor approach here. So I need the cube root of 27. So again, I want to do the prime factorization of 27. And of course, as you can tell, if you haven't sensed, you really need to know your math facts. You really need to know your times tables going forward and backward. So that's of the essence. If you don't, then you need to prepare for that by practicing with it. It's not too late. You can do it. So we've got 27. I want the prime factorization of 27. I'm thinking of 2 numbers, any 2 numbers that equal 27. The first 2 that come to my mind is 9 times 3. I'm going to break down the 9 to be 3 times 3, and 3's are prime numbers. Okay, there's my 3. I can't break it down any further because 3 is just a prime number. So, since the index is 3, for every 3 values of 3 factors that I have of the same number, I'm going to take 1 out. So here's 3 3's, and I'm taking 1 out, and it's this 3. And that's how we arrive at the cube root of 27. Okay, how about something like negative 125? Now we are allowed to have the negative sign because it is an odd index number. So I can take the negative 125 or 125 and break this down being the prime via the prime factorization. So what are 2 numbers that equal 125? All right, well, let's see. I've got 5 times 25. 5 is a prime number, so I'll just circle it. And 25 breaks down to be 5 times 5. And here are 3 5's. So for every 3, I want to take 1 out. And notice, they're all negatives too. Because negative times a negative is a positive, and then a positive times this negative here would be a negative. So I end up with a negative 125. All right, therefore, the cube root of negative 125 is negative 5. Okay, how about the cube root of 8 over 125? Well, that one we just did, so I could say, what's the cube root of 8? I'll take the 8, do the prime factorization for it. I've got 4 times 2. 2 is prime, and 4 breaks down to be 2 times 2. And those two 2's are prime. So notice I've got 3 2's. For every 3, I'm going to take 1 out. And there's the 1 I'm taking out. The 125 we just did above, only it's positive, but the factors are almost the same, being the absolute value of negative 125. So 125 is going to be 5 times 25. Real quick, here's my prime number 5. 25 breaks down to be 5 times 5. So there I'm getting positive values. For every 3, I take 1 of them out, and there's my 5 in the denominator, where I end up with 2 over 5. Okay, how about this fella here? I got negative 8, x to the 9. So I could do this, look at this separately. I got negative 8. Well, we just did positive 8 up here, but I've got negative 8 and then x to the 9. So if I do the prime factorization for this, I know this negative 8 is going to come from negative 4 times 2. I'll break it down this way for us. 2 is prime. And then I've got negative 4. Negative 4 breaks down to be 2 times negative 4. No, negative 2. Okay, so I've got 3 values that are not quite the same though. I got this listed as positive, this is positive, and this is negative. But they can all be negative though. Would you agree? Negative times a negative is a positive, and the 3 negatives equal a negative. So therefore, this is where the negative 2 comes from. The cube root of negative 8. Then I'm thinking, what's the cube root of x to the 9? Well, that means x times x times x, x times x times x, and 3 more. There's 9 of them. 3, 6, 9. Be official here. Okay, since the index number is 3, then for every 3, I'm going to take out 1. For every 3, I'm going to take out 1. Well, I'm going to take out 1 here. I'll put it over here. So I had my negative 2, which is here. I'll write that back down here, times x, and here's 3 more x's here. So I'm going to take 1 of those out and bring it over here as part of my answer. And then I got 3 more here. They went in evenly. So I got 1 more x that comes out here. So this ends up being negative 2x to the 3rd, which is what they've got. And that's where they're getting it from. Okay. Here is a very important concept here. Other roots can be found as well. The nth root of a is defined as, notice in our letter formations here, the nth root of a, where n is a very important number. That tells us how many of each of the factors, when we do our prime factorization, of the numbers that are the same that we take out. Okay, equals b, only if b to the n equals a, which is kind of like the converse of exponential notation or exponential form. B to the n. So the exponent becomes the index. Okay, let's see. I could do you some examples here. However, I think we've got some that are possibly coming. All right, let's hold on and see what we've got. Okay, and here's what we're talking about. Find each root. Notice, this is what's the sixth root of 64? What's the fifth root of negative 32? What's the fourth root of negative 16? Okay, they have their answers here, but I'm going to show you how to find them. All right, let me show you how to find those answers. So, and others too, maybe. I'll add up a few more. So here I've got 64 is the number. 64. I want to do the prime factorization. I'm going to write this here because this is really important for when you're stuck, if you're not sure what to do. All right, the prime factorization is 64 is going to be, well, what two numbers are equal 64? 8 times 8. And then the 8 I can break down to be 4 times 2. I know 2 is prime, so I'll circle it now. And the 4 breaks down to be 2 times 2. All right, so here I've got 3 2's. And this 8, I must have 3 2's. 2 times 2 times 2. After you do this for a while, you'll start remembering what the square roots of certain numbers are, what cube roots of certain numbers are. Okay, so that's an advantage to you. Okay, so here I've got 3 more. And so that means I've got 6 of them. I've got 6 2's. I'm going to rewrite it out here. You won't have to do this. You can use your own idea for saving writing in your own way. So here I'm going to write it out, 6 2's. And for every 6 of them, I'm going to take 1 out. So that's what I've got here. There's 6. And I just take 1 of these 6 out, and that's how they're getting 2. That's why the index number is important to remember. How many of the same number am I taking out? How many of the same number am I circling? This is saying 6 of them. For every 6, I take 1 out. Here's 5 to the negative 32. Well, this is an odd number, index number, and this is negative inside. Is that okay? Yes, that's okay, because an odd amount of negative numbers equals an odd number. All right, so I want to break down the 32. I know it's negative, so I can leave that alone. 32, what are two numbers that equal 32? I'll say 8 times 4. And boy, I'm noticing it already. 8, I've done 8 up here already, so I know that's 3 2's. Whoop, that's a squiggly 2. 2 times 2 times 2, I've done it already before. And now I'm going to do the 4, which is 2 more 2's. So here I have 3 and 2 is 5 2's. What's my index number happens to be 5. So that means for every 5 2's, you take out 1. And there it is. And remember, it's negative 32, so it's okay to make that negative 2 as well. And then finally, we've got this notion here. Oh, I have a even index number with a negative number underneath the radical sign. This is not possible. Okay, so just as it says here, is not a real number since the index 4 is even and the radicand negative 16 is negative. There is no real number that when raised to the 4th power gives negative 16. Okay, so remember that. That is not possible. Okay. All right, let's try these examples here. Simplify. Assume that the variables represent any real number. Okay, so we've got something going on here to the tune of... I took the answers away, and then we'll figure out what the answer is. How about that? All right, here's the square root symbol, the radical sign, and notice the index isn't there. So when it's not there, we are to know that it's really 2, because this is the square root. And they want to know what the square root of negative 4 to the second power is. Well, notice that the exponent on the inside of the radical is equal to the index number. So this is negative. My answer is going to be negative 4. I'm sorry, it's going to be positive 4. Notice under the radical sign, negative 4 squared equals 16. So this is the same thing as saying it's what's the square root of 16. And we know that's to be 4. Okay. How about this one? If I follow the rule I was doing earlier, where I'm going to say this is x minus 2 to the 4th power, if I did the prime factorization of that, x minus 2 to the 4th power, the prime factorization, now it's kind of silly, seems silly, but if I did the prime factorization, it would be what? X minus 2, really drawing this out, but I want you to see what's going on. X minus 2 and x minus 2. Isn't that what x minus 2 to the 4th power means? It means 4 of these. And since the index number is 4, that's going to translate to say that for every 4 factors of x minus 2, I'm going to take out one of them. Well, that's all I've got. 1, 2, 3, 4. So I'm going to take out one of them, and it's x minus 2. And that's what is that, 4th root of x minus 2 to the 4th power is. So what do you think this is going to happen here? I've got 5 of these 2x minus 7s if I laid it out like I did for the x minus 2s. And it's the 5th root, so for every 5 I'm going to take out 1. So my answer just remains the 2x minus 7, one of them. Gets to be kind of fun after a while. How about 25x squared? Here, just the index is 2. We know that. So the square root of 25 is 5. What's the square root of x to the 2nd power? Think about that. There's my index number. It's x to the 2nd power. So x to the 2nd means x times x. For every 2, I'm going to take out 1. So I get 5x. Which makes sense too, right? Because 5x in parentheses raised to the 2nd power equals 25x squared. I want to look at it that way. All right, next job. All right, let's check this out. I've got something that's saying simplify the following and assume that all variables represent positive numbers. All right, so here I've got the 4th root of 16x to the 8th. All right, so let's start off by doing the prime factorization of that 16, of this 16. Come on, 16x to the 8th. I'm going to do the prime factorization. I'm going to do it separately if you need to. So 16 is going to be 8 times 2, taking any two numbers that equal 16. And there's my 2 prime, that's prime, and here's my 8 again. Boy, that comes up a lot, right? I'll do it one more time as 4 times 2. Here's my 2 prime, and the 4 breaks down to be 2 times 2. So let's say from now on, when we see the cube root of 8, that we know it's 2 times 2 times 2 without doing that factor tree with a 4 in it. Okay, so altogether I've got 2 times 2 times 2 times 2, which is 16. And then the 8, well, that's easy. I know I'm going to have 8 of them. So I got 3, 4, 5, 6, 7, 8. Okay, 4 and 4. All right, so now what is this telling us? The 4th root of 16, 8 to the x. So that means for every 4 2's, I'm going to take out 1. Or any 4 of any of the same number or variable I'm going to take out. as these numbers get bigger. So here I've got 4, 2, so one of them comes out. I'll put it there. And then the x to the 8th, for every 4, I'm going to take 1 out. Well, here's 4 x's here, so I'm going to take 1 out. And here's 4 more here. I'll take another x out. And I'll write it up as squared. X times x, or x squared. So there's my 4th root of 16x to the 8th. Okay? Make it a project. Make it fun. All right, what's going on here? This is, so we know our notation here. This is a negative sign. This is a negative sign. Negative in front of the radical, not a negative 5 here for the index. The index is just 5, positive 5. All right, and then we've got negative on the inside. Is that okay? Yes, that's okay, because the index is odd number. All right, so what we want to do is the prime factorization. Let's say I got numerator, denominator here. This seems a little more complex, but we can handle it. All right, so let's take the 32, a to the 5th. 32, a to the 5th. And the prime factorization is going to be what? 8 times 4. Here's my 8. Again, boy, that comes up a lot. You'll notice that. That's 2 times 2 times 2. And the 4 is 2 times 2. So these are all prime numbers, so that's good. Then the a to the 5th, that's easy too. That's 5 a's. 3, 4, 5. I'll just do it this way. Okay. So for my, let's just take care of our numerator. I like to do things like that. So I need the 5th root of 32. Here's my 32. For every 5 2's, I'm going to take 1 out. Well, there's 5 of them. So 1 comes out, and I'll put that in the numerator. And same with the a. I got 5 a's, so 1 of those come out. So I've got 2a. And then that's going to be over b to the 15th. Well, b to the 15th. Let's try that. Do I have to write this out 15 times? I will for you, just so you get it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 of them. All right, it's to the 5th root. So therefore, b to the 15th, for every 5 b's, I'm going to take 1 out. 1, 2, 3, 4, 5. Take a b out. I'll put it down here, b. 1, 2, 3, 4, 5. Take another b out. 1, 2, 3, 4, 5. Take a third b out. So here I got b times b times b is b to the 3rd. And that's what this becomes. And what am I forgetting? I'm forgetting the negative here, because these would all be negatives here, technically. Okay, so that would go here. And then it is, I'll put these in parentheses, right? And the negative on the outside. So in fact, it ends up being how much? Positive 2a over b cubed. That's what happens when two negatives are multiplied together. All right, so that was fun. Hopefully you won't have to go through all that, but you'll get, and notice the 32 had 5 2's in it. 4 2's is 16. So hopefully you'll remember these after a while. Memory. Okay, something of importance here, where we have an equation here that is actually a function. Since every value of x that we substituted into this equation produces a unique value of y, unique meaning never the same, the root relation actually represents a function. The domain of the root function when the index is even is all non-negative numbers. The domain of the root function when the index is odd is the set of all real numbers. All right, so we will see that forthcoming. In particular, the domain of the root function when the index is even. It's all non-negative numbers. So you'll see that in the graphing form coming up. Okay. All right, we have previously worked with graphing basic forms of functions so that you have some familiarity with their general shape. You should have a basic familiarity with root functions as well. And we're going to go over a couple of them on the next screen. Okay, here's an example. A couple of things I want to point out to you as we're doing these. Graph y equals the square root of x. All right, in the example here from the textbook, they're giving us some values here that I want to discourage you from using. Because if I substitute 6 in for x, this is the t-chart here, then I got to know what is the square root of 6. All right, and it answers this square root of 6. The answer is the square root of 6, but I don't really know where that is on this number line. Not readily. You could punch it in your calculator and find out. You could do all this with your calculator, really, but it's more fun to do this manually. Get a deeper, richer understanding of what's happening. So in the case of this, I don't want to even use this, so scratch it off. I'd prefer to use something like 4, because I know what the square root of 4 is. The square root of 4 is indeed 2, right? So if we're substituting 4 in for the x, they're asking what is the square root of 4? And I know it equals 2. So when x equals 4, y equals 2. I can plot that. When x is 4, y is 2. So I know it's here. Because we're graphing this equation. And I want you to take note of the shape that it's in. All right, don't forget our favorite one, 0 and 0. Okay, that's the second one. I need more than 2, though, because the line is curved. I don't want to just draw a straight line. That's incorrect. This line is actually curved, as you will see. So I could say when x is 1, that's a square number. When x is 1, y is 1. So that'd be over 1, up 1. Okay, you can see the curve going in there. That's not bad to use there. But I want one more. And it's not going to be 5. It's not going to be 6 because they're not perfect square numbers. It's not going to be 7. 8, not going to be. But 9 is the next one in line. And I can say when x is 9, here's 9 over, I'll just say 9 is here. Y is going to be 3. And that kind of gives me enough to draw my line and graph this equation. Okay? So when you come up to a problem like this, you want to think in what is going to give me a whole number answer for the square root symbol. Think about it when you're doing it. All right, next. All right, here is another one, but this is to graph the cube root of x. Cube root now. All right, so what does that mean? I need values, numbers that are cube roots. For example, the cube root of 1 is 1. The cube root of 3 is 8. The cube root of 3, I'm sorry, I'm saying that backwards. I'm going backwards. Exponentially. 1 to the third power is 1. 2 to the third power is 8. 3 to the third power is 27. 4 to the third power equals 64. And let's do one more. 5 to the third power, which is 125. Okay, so when we're graphing this, notice I'm taking the small numbers, and 0. 0 to the 0 power is 0. Okay, so I've got this going on, numbers 1 through 5, so I can stay on the map here. I don't want values that are any larger than that. So let me erase these if I can. Get them off the board. Okay, and I'll use those values here to do my graphing. So in other words, if I say x, when x is 0, well, the cube root of 0 is 0. Okay, and I can plot that point at 0, 0, wherever that line is. Looks like it's here. All right, how about when x is 1? Y is going to be 1. So those are two guarantees. 1 and 1. I'm going to go up 1 and down 1. And what else do I know here? I could say, how about when x is not 4 this time, because that was the square root. Now I got to go all the way up to not 5, not 6, not 7, but 8. When x is 8, what's the cube root of 8 is 2. Cube root of 8 is 2. Because 2 times 2 times 2 is 8. And how about, let's do one more. Maybe 2, maybe more. Let's see. So now after 8, what's the next cube number? Is it 9, 10, 11, 12, 13? I could take it this way. 1 to the third power, 2 to the third power, 3 to the third power. So when 3 to the third power is 27, that was our next cube number. When x is 27, y is going to be 3. But 27 presents a problem because it's way off the board. So in this case, notice I'm using the cube. I want the cube root of this x. So this could involve negative numbers as well. So I could say when x is negative 1, what would y be? Negative 1 as well. When x is negative 8, y would be, the cube root of negative 8 is negative 2. And I can stop there. I will not use this one because this takes me way off the board. So I will plot these points here. I got 0, 0. I got 1, 1. How about 2, 8? I'm going to go, how about 8, 2? I'm going to go over 8 and up 2. So that gives me a nice line here to draw. Down on the other side, the negative way, I could say negative 1 and negative 1 is here. Let's see, here's this. So this graph is kind of goofy a little bit, but there's negative 1, and negative 8, negative 2. So negative 8 is this way, and down 2 this way. So you can see the symmetry here. So I could draw this line going this way, down, and then back this way, and then over to. So there's a general idea what that graph looks like. So this is a graph of a cube root. And there you have it. Notice the numbers I picked, though. I couldn't go very far, though, could I? But I can still draw this within reason. Okay. What the heck? All right, here is some examples that we missed for some reason or another. So I'll go over with them with you now from page 684 in this section 10.1. All right, remember our functional notation and how it works, where we have two functions, f and g. In this case, that's the name of the functions. One's f and one's g. And this is talking about what is f of 8. So again, this refers to the f function. And when we replace x with 8, what does that function equal? So it's just a matter of plugging in and computing. So if x is 8, we'll just say 8 minus 4, which equals the square root of 4, which equals 2. Okay, that was pretty nice. The next one is f of 6, so we do the same thing. And now I'm going to replace the 6 with the x, so this is going to be the square root of 6 minus 4, which equals the square root of 2. Okay, so they've got the square root of 2, and the exact answer is the square root of 2. All right, they don't want an approximation. If they did want an approximation, they would say so. Approximate the value. What is the square root of 2 approximately? All right, how about g of -1? Now we're switching functions over to g, and I'm going to substitute -1 for the x only. So this is the cube root. So I'm going to have the cube root of -1 plus 2, which equals the cube root of 1, which equals 1. Lastly, I'm going to have g of 1 for the g function. Again, that's the cube root of 1 plus 2. And the cube root of 1 plus 2, which is 3, equals the cube root of 3. Now I leave it as such. All right, and again, that's a matter of plugging and playing. All right, that's it for section 10.1. See you as we venture ahead to 10.2. Bye.